Hello and good day, everyone. So today you'll be learning about substitution and elimination, which involve reaction of alkyl halides. So in this topic, we will discuss on SN1, SN2, E1, and E2 reactions. First, let's look on some naturally occurring alkyl halide. So there are several marine organisms, including sponges, corals, and algae, which they can synthesize organohalides, a halogen-containing organic compounds, which they use to deter predators. One example is red algae, which they can synthesize a toxic phosphating organohalide that keeps predators from eating them. However, there is one predator that cannot deter from this organohalide is a mollusk called a sea hare. So after consuming the red algae, the sea hare can convert the original organohalide into a structurally similar compounds, which they use for its own defense. So unlike other mollusks, a sea hare does not have a shell. Its method of defense is to surround itself with a slimy material that contains the organohalide, which thereby protecting itself from carnivorous fish. So this is the structure of organohalide that's synthesized by red algae. So the bottom is the organohalides that's synthesized by sea hare after consuming the red algae. So you can see both structure are basically similar. So now we move on to the reactions of alkyl halides. So usually we use RX in the short form. So we will look on the SN1, SN2, E1, and E2 reactions. So you can see on the left, there is examples of several alkyl halides. So you can see carbon that link with methyl link with fluorine, with chloride, bromide, and iodine. So basically, this carbon we call alpha carbon, which is attached to the alkyl halide, where it is actually an electrophilic electron or electron accepting, which either of or both of two reasons. The first reason is the carbon or the alpha carbon that linked to the alkyl halide is polar, which making it positive charge. It is because the electron negativity of the halide is more. For example, fluorine is 4. So carbon electron negativity is 2.5. So when you minus is 1.5. So we can see that the fluorine is very high electronegativity. And then chlorine, the electronegativity is 3 minus by carbon 2.5 is 0.5. And then bromine 2.8 minus 2.5 is 0.3. And lastly, the electronegativity of iodine is similar to carbon. So the electronegativity is 0. So you can see that when there is the electronegativity of the halide is more than the carbon, so the alpha carbon will be positively charged. The second reason is that the halide, for example, the chloride, bromide, and iodide is a good leaving group. So you can see at the bottom here. So to the left, this is the best leaving group because they are the weakest base. So started with iodide, bromide. You can see that they are very weak bases. So when they are decreasing basicity, they are increasing instability. All right. So to the right, they are the poorest leaving group because they are very strong bases. For example, fluorine and hydroxyl. So now we look on some example of leaving group ability. So it is electron withdrawing. So stable once it has left, not a strong base. So it's a polarizable to stabilize the transition state. Below are two types of leaving group. So the first one is ions, which is chloride, bromide, iodide, sulfonate, sulfate, and phosphate. And below you can see neutral molecules such as water, alcohols, amines, and phosphine. Now let's move to reactions of alkyl halide, SN1, SN2, E1, and E2 reactions. So first we need to know some basic. When a nucleophile, is this an electron donor, example hydroxyl, reacts with an alkyl halide, so the halogen will leave as a halide. So this is nucleophile. When it's attacked, usually R is the alpha carbon that bind with the halide. So the halide or the bromide will be released. So there are two competing reactions of alkyl halides with the nucleophiles. The first, we call it substitution. So you can see here that nucleophile, usually they will attack the alpha carbon that attached to the halides, right? Then the nucleophile will replace the halogen on the alpha carbon. So it will release the halide. Another reaction is elimination, when the nucleophile will attack the hydrogen at the beta carbon, which is adjacent or beside the alpha carbon. And then later, the halide will be released and bind with the hydrogen. So the nucleophile will remove the hydrogen from the beta carbon and the halogen will leave, forming an alkene structure. So next, we need to look on the substitution. So there are two kinds of substitution reactions, which called SN1 and SN2. So as well, there are two kinds of elimination reactions, which called as E1 and E2. So we need to study the SN1 and SN2 first. So SN2 stands for substitution, nucleophilic bimolecular. Another word for bimolecular is second order. So bimolecular or second order means that the rate of the SN2 reaction is directly proportional to the molar concentration of two reacting molecules. The alkyl halide is the substrate and the nucleophile. So this is the equation. Rate is equal to the K constant times the concentration of alkyl halide or the substrate times the concentration of nucleophile. The mechanism of SN2 reaction is the one that we shown below. So we can see previously that nucleophile will attack the alpha carbon that adjacent or link with the halide, and it will substitute the halide, right? So note that the nucleophile must hit the backside of the alpha carbon. So the nucleophile to carbon bond forms as the carbon to the halide bond is breaks. So no carbon cation intermediates are formed. So we can see another example in the next slide. So this is an example of bromomethane react with the hydroxyl to produce methanol and release bromide. So if the concentration of bromomethane is doubled, the rate of the reaction is doubled. So if the concentration of methanol is doubled, the rate of the reaction is doubled. So if concentration of the bromomethane and the methanol is doubled, so the rate of reaction is quadrupled. So based on the statement or the law of SN2, so the equation of rate is equal to the K constant times the bromomethane concentration times the concentration of nucleophile or the hydroxyl. So this reaction is an example of SN2, which is S is for substitution, N is stand for nucleophilic, and 2 is stand for bimolecular. All right, so we look back again on the second order or SN2 reactions. So hydroxyl is a very good nucleophile. We react with the alkyl halide, where it will attack at the back of the alpha carbon to produce a transition state. And at the end, the bromide will be released and the hydroxyl will be substituted at the position of bromine. So the rate of accentuation will depend on 4 factors. The first one is the nature of the substrate or the alkyl halide. So the second one is the power of the nucleophile. The third one is the ability of the leaving group to leave. And number 4, the nature of the solvent. So in this topic, we will discuss all these 4 factors that will affect the accentuation. So the first one, we should consider the nature of the substrate. So the unhindered alkyl halides, those in which the backside of the alpha carbon is not blocked, will react fastest in SN2 reactions. So that is, methyl is more or faster than primary, and the primary is faster than the secondary, and lastly, tertiary. So while a methyl halides react quickly in SN2 reactions, a tertiary does not react. So the backside of the alpha carbon in a tertiary alkyl halide is completely blocked. So we can see from this figure, so the upper part, methyl bromide. So you can see from these space filling models, you can see that the backside of this alpha carbon, the yellow model space, right, is unhindered, right? Second one is ethyl bromide. It is a primary alkyl halide. The backside of this alpha carbon is slightly hindered. The third one is the isopropyl bromide. The backside of this alpha carbon of the secondary alkyl halide is mostly hindered. And lastly, T-butyl bromide, where the backside of this alpha carbon of this tertiary alkyl halide is completely blocked. So basically, right, the SN2 reactions, right, it will be decreasing from methyl to primary to secondary and lastly tertiary due to this alpha carbon that been hindered, right, by the structure. And then you can see the effect of the nucleophile on the rate of SN2 reaction on this vinyl bromide and bromobenzene. So we can see that the alpha carbon in vinyl and aryl halide is considered as tertiary carboxyl ion, which is completely hindered. So basically, you can see that from this figure below, the nucleophile cannot attack at the back of the alpha carbon because it's being hindered, right, by the structure, the CH2 in front of the alpha carbon, as well as this bromobenzene. So it has totally been or completely been hindered. So this is due to the overlapping of p orbitals that form the pi bonds in vinyl and also aryl halides, which completely block the access of the nucleophile to the backside of the alpha carbon. Second factor that we should consider is the power of the nucleophile. So the better the nucleophile, the faster the rate of SN2 reactions. So below is a table that shows the relative power of various nucleophiles. So the best nucleophile are the best electron donors. So you can see the reactivity from very weak to very good nucleophile. So we can see that an example of very weak is mostly there are acids. For example, like sulfuric acid, phosphoric acid, acetic acid, which the relative reactivity is below 0.01. And then we can see basically alcohol, they are very weak. Pair nucleophile, so fluoride, an example, chloride. Alright, so ammonia, good example of nucleophile are bromide, hydroxyl. And we can see the most or very good nucleophile are cyanide. And we can see sulfuryl, thiol. So this is 3-methyl-phosphine, right? An example of amine or magnesium with halide, iodide, and hydrogen ion, right? So which they have relatively very high reactivity, more than 100 times 10 power of 6. And then the third factor that we should consider is the nature of the living group. So the living group usually has a negative charge. So the group which best stabilize a negative charge are the best living groups. So the weakest bases are stable as an ion and are the best living groups. Weak bases are readily identified and usually they have high pKb values. So you can see here from the left, iodide is the most living group, which is it has the value of this bases is very weak, right? Then the pKb is 23, which is very high in pKb value, and the least pKb value is the most or the strong base, right? From iodide to bromide to chloride and to fluorine, the living group ability is decreasing. So you can see the statement below. Iodine is a good living group because the iodide is basic. And the hydroxyl group, you can see here, is a poor living group because the hydroxide is a strong base, followed by the RO, or the oxygen, and also the amine is very strong base. Lastly is the fourth factor that we should consider on SN2 is the nature of the solvent. So there are 3 classes of organic solvents. So the first one is protic solvents. For example, which contain the hydroxyl, the amine groups. There are protic solvents which can slow down the SN2 reactions. The second one is polar aprotic solvents. For example, acetone, which contains strong dipoles but no hydroxyl or amine group, which this polar aprotic group solvent can speed up the SN2 reactions. And the third one is non-polar solvents, for example, hydrocarbons, which is the SN2 reaction are relatively slow in non-polar solvents. So you can see from the 3 different classes of organic solvents, the protic solvents and the non-polar solvent will cause slowdown the SN2. However, the polar aprotic can speed up the SN2 reactions. So we can see from this explanation below why protic solvents, example, water, methanol, ethanol, and acetic acid, cause the slowdown of SN2 reaction because it clusters around the nucleophile, or we call it solvate, the nucleophile, and it causes it lower its energy through stabilize it and reduce its reactivity by hydrogen bonding. So for example, here in the middle is the halides and the surrounded by the protic solvents, for example, water, right? So it will cause the solvation or solvate the anion nucleophile, which reduce the nucleophilicity and reduce the reactivity and increase the stability. So a solvated nucleophile has difficulty hitting the alpha carbon. However, for the polar aprotic solvent, So they can solvate the cation counter ion of the nucleophile, but not the nucleophile. For example, acetonitrile or acetone. Right? And other example is dimethyl formamide, dimethyl sulfoxide, hexamethyl phosphoramide, and dimethyl acetamide. So this polar aprotic solvent solvate the metal cation, which leaving the anion counter ion or nucleophile bare and thus more reactive. For example, this structure, so the sodium ion, right, react with this acetonitrile of the alkyl halide. So it will cause the nucleophile of the structure of the sodium hydroxide will be bare, right? So it open up so that the nucleophile will be more reactive, right? So however, non-polar solvent, for example, like benzene, carbon tetrachloride, hexane, they do not solvate or stabilize nucleophile. So SN2 reaction are relatively slow in non-polar solvent, similar to that in protic solvent. So example, benzene, carbon tetrachloride, and hexane. And another effect of SN2 reaction is steric effect. So you can see the primary of the alkyl halide, the energy or the activation energy is low. However, at the secondary alkyl halide, the activation energy is increasing. And usually the reaction of the SN2 reactions, for example, the neutrophile of hydroxyl, which react with the S2 bromobutane, so it will be inversion, or the configuration will be invert to R2 butanol when it's caused the SN2 reaction occurred and release the bromide ion. So if you look on this slide in your notes, so basically the bromobutane is actually S configuration and the 2-butanol is R configuration. Next, we move on to the first order nucleophilic substitution reaction, or we call it SN1 reaction. So we can see here that this is a tertiary structure of alkyl halide, which can react with the sodium iodide in rapid reactions to form the alkyl halide substituted with iodine and release the sodium and bromide. So the tertiary alkyl halide are essentially inert to substitution by the SN2 mechanism because of the steric hindrance at the back of the alpha carbon. So despite this, the tertiary alkyl halide do undergo nucleophilic substitution reactions quite rapidly, but by a different mechanism. Example, we call it as SN1 mechanism. So SN1 is a substitution nucleophilic first order unimolecular. SN1 reaction obeys the first order kinetics, which is rate is equal to constant times the concentration of the alkyl halide. So the rate depends upon the concentration of only one reactant, the alkyl halide, not the nucleophile. So the order of reactivity of substrate for SN1 reaction is the reverse of SN2. So meaning the tertiary is higher or faster than the secondary compared to the primary, vinyl, phenyl, and lastly, methyl. So below are some of the examples of the tertiary, secondary, primary, vinyl, phenyl, and methyl. So you can see that the increasing rate of SN1 is from tertiary towards methyl, which is reverse to the SN2. right? The substitution reaction of SN1. So we can see from this example, 1-bromo-1,1-dimethyl ethane react with water will form 1,1-dimethyl ethanol and release the bromide in the form of HBr. So the concentration of 1-bromo-1,1-dimethyl ethane is doubled. The rate of the reaction will be doubled. However, if the concentration of the products, 1,1-dimethyl ethanol, is doubled, the rate of the reaction is not doubled. So the rate law of SN1 is rate is time is equal to the constant of concentration of the 1-bromo-1,1 dimethyl. So this reaction is an example of SN1. So where S is stand for substitution, N stand for nucleophilic, and 1 stand for unimolecular. So now let's look on the mechanism of SN1 reactions. So for example, this tertiary alkyl halide containing bromine. So we know that it will form or we substitute with the iodide to form the sodium and bromide will be released. So in the differences between SN1 and SN2, SN1 will involve two steps. The reaction step is the first one, it will be slower, or the rate limiting dissociation of the alkyl halide will form a cation intermediate. So you can see that this bromine is being ionized and it will release the bromine in the first step. Once the bromide is released, so it will form a carbon cation where a rapid nucleophilic attack will be occur on the carbon cation. So that's why the first step is causing the slower or the rate limiting dissociation due to the bromide to release in the first step. And the second step will be rapid, where the nucleophilic attack by the iodide very rapid towards the carbon cation on the second step. So you see that the nucleophile here is not involved in the slower or rate limiting step as compared to in the SN2 reactions. So now let's look on the rate of SN1 reaction one by one. So the rate of SN1 reaction will depend upon only three factors. So the first one is the nature of the substrate or the alkyl halide. The second is the ability of the living group to live. And the third one is the nature of the solvent. So you can see the rate is independent of the power of the nucleophile as compared to SN2. So we look on the first one or the first factor that we should consider the nature of the substrate. So the highly substituted alkyl halide or the substrate will form a more stable carbon cation. So we can see from the example previously that tertiary will be more stable as compared to secondary, primary, and methyl to form carbon cation. So therefore, the tertiary alkyl halide will have a higher increasing rate of SN1 reaction as compared to secondary, primary, and methyl. First, we look on why the stability of carbon cation is very important in SN1. So first, we can see that the tertiary structure of alkyl halide, the inductive effects of these alkyl groups donate shift of electron density through the sigma bonds to electron deficient atoms. So this will stabilize the carbocation. So alkyl groups are weak electron donors. So they stabilize carbocations by donating the electron density by induction through these sigma bonds. And then the second effect is due to the carbocation is stabilized by the hyperconjugation by partial overlaps of the alkyl carbon to hydrogen bonds with the empty p orbital of the carbocation. So we know that at this position, the p orbital is empty or is a vacant p orbital of carbocation, which will be linked, right, by through stabilization of hyperconjugation, overlap of hyperconjugation towards the carbon to hydrogen of the empty p orbital of the carbocation. Another cause or effect of stability of carbocation is the primary allyl carbocation and secondary allyl carbocation. So this allyl and also the other one, benzyl halides, also react quickly by SN1 reaction because their carbon cation are unusually stable due to their resonance, right, form which delocalize charge over an extended pi system. So we know that this alkene is very stable, right? And also this secondary allyl, of course, the benzyl halide, we know that is a delocalized charge over this structure, which make them unusually stable due to the resonance. The primary and the secondary benzylic are very stable in the carbon cation. So now we look on their relative carbocation stability. So we can see these are the three different structure. So the first one, we know that this is the alkyl halide, the tertiary, secondary, primary. So the strength of SN1 is from tertiary towards methyl. However, you can see from the upper and the bottom of the benzylic, the tertiary and secondary and primary benzylic, it is more higher than the alkyl halides, as well as for tertiary allylic and secondary and primary allylics is even higher, which is similar to the benzylic carbocation structure. So you can see the increasing of carbocation stability and rate of SN1 reactions based on the benzylic and allylic as well as the tertiary structure. So note that the primary allylic and primary benzylic carbocation are about as stable as secondary alkyl, right? You can see here. And then the secondary allylics and secondary benzylic carbocation are about as stable as the tertiary alkyl. So you can see from this figure. And then you note that the tertiary allylic and the tertiary benzylic carbocation are more stable than the tertiary alkyl carbocation. And you can also note that the phenyl and vinyl carbocation are unstable, where these two, they do not or usually not react through SN1 or SN2 reactions. All right, now we move on to the second consideration on the factor of SN1. So the second one is on the nature of the living group. So you can see here, this is example of leaving group started from iodide, bromide, chloride, fluoride, hydroxide, the oxygen, and the amine. So you can see that the pKb value is higher to the highest leaving group because of they are very weak bases. So the nature of the leaving group has the same effect on both SN1 and SN2 reactions, right? The better the leaving group, the faster a carbon cation can form, and hence the faster will be the SN1 reaction. Right, so the leaving group usually has a negative charge, and group which best stabilize a negative charge are the best leaving groups. The weakest bases are stable as an ion and are the best leaving groups. Right, so weak bases are readily identified, so they have high pKb values. And you can see basically the leaving group ability is similar to SN2, right? Started from iodide towards the amine. And the iodine is a good leaving group because iodide is non-basic. And the hydroxyl group is poor leaving group because the hydroxide is a strong base. All right, and then the third factors that will be involved that affect the SN1 will be the solvent. So the relative rate of SN1 reaction due to the solvent effect are given. So you can see below the alkyl halide, the tertiary structure react with, for example, alcohol to form the ethanol and acid, hydrochloric acid. So you can see that the reaction of SN1 will be more effective in water, right, as compared to ethanol, 20%, meaning it's dissolved in water 80%, and you increase more or less water, 60% of water and 40% of ethanol, it will decreasing the SN1, and lastly the 100% ethanol will be lesser. So you can see the nature of the solvent for SN1 reaction. So for SN1 reaction, the solvent will affect the rate only if it influences the stability of the charge transition state, which is the carbon cation. So the nucleophile is not involved in the rate determining step. So solvent will effects on the nucleophile do not affect the rate of SN1 reaction. So the polar solvents, both protic and aprotic, will solvate and stabilize the charge transition state of carbon cation intermediates, lowering the activation energy and accelerating the SN1 reactions. So however, non-polar solvents do not lower the activation energy and thus make the SN1 reaction relatively slower. So this is to show you the differences between the polarity and the rate of reactions in SN1. So now we look on the solvent, example of a solvent on SN1. So you can see there is several examples of aprotic solvents and protic solvents. So you can see that the non-polar solvent and the aprotic solvent hexane has the lowest dielectric constant, and the highest is the MSO, 48, while protic solvent, acetic acid, is the lowest as a dielectric constant, and the highest is water, 80.4. So solvent polarity is usually expressed by dielectric constant, or epsilon, which is a measure of the ability of a solvent to act as an electric insulator. So polar solvents are good electric insulators because their dipoles around surround and associate with the charged species. So dielectric constant of some solvent are given in the following table, which is showing just now that the hexane is the least and diameso is the most in the aprotic solvent. And in protic solvent, acetic acid is the lowest and water is the most, as considered as the most dielectric constant of solvent based on polarity. All right, even though that the nucleophile has no effect on SN1 reaction, we should also look on the effect of this nucleophile. So with the example of these two reactions of alkyl halides, tertiary bromide with the sodium iodide and potassium fluoride. So both will produce or substituted. For example, like the alkyl halide with the bromide will dissociate with the iodide, and the tertiary that containing the bromide will dissociate with the fluoride, right, to form sodium bromide and also potassium bromide. So if you look these two, the differences is the nucleophile, and both will be react at the same rate, right? So by considering the nature of nucleophile of SN1, so we should recall that the nature of nucleophile has no effect on the rate of SN1 because the slowest rate determining step of SN1 reaction is the dissociation of the leaving group and the formation of the carbocation ion, right? And all carbocation ions are very good electrophiles or electron acceptors, and even weak nucleophile like water and methanol will react quickly with them, right? So the two SN1 reaction, the one that I explained previously, these two below, will proceed at essentially the same rate, since the only difference is the nucleophile. So next we look on the mechanism of SN1 reactions. So we can see there are two differences on the left and right. So you can see on the right there is same configuration, right, of the alkyl halides after react with the nucleophile, right, where the position is the same, right. However, on the left, there will be a inverted of the configurations relative to the alkyl halides. So in SN1, the inverted configuration will occur. So now we can see the differences clearly between this SN1 and SN2. So SN1, there are two-step mechanism. SN2, only one step, right? So SN1 is a unimolecular rate determining step, right? Which is involve only the alkyl halide or the substrate. SN2 is bimolecular rate determining step, which we have to consider in the rate, the alkyl halide and the concentration of nucleophile. And the products for SN1 have both retained and inverted configuration relative to the reactant, while SN2, the product has to be inverted in the inverted configuration relative to the reactants. And you can see very clearly for SN1, the reactivity order is started from tertiary, secondary, primary, and methyl halide. While SN2, the reactivity order is started from methyl, primary, secondary, and tertiary. For SN2 is basically on the hindered alpha carbon, and for SN1 is based on the carbon cation formation. Now we move on to the elimination reactions, E1 and E2. So basically we have seen this reaction before, right? Where this, we consider hydroxyl group can attack at the back of the carbon, right? Where it will release the halide to form the alcohol, where this is the transition state. Right, so we have seen that the alkyl halides may react with basic nucleophiles such as sodium hydroxide via substitution reactions. Okay, and at the bottom, so also we can recall our study of preparation of alkenes, right? When secondary and tertiary alkyl halide is treated with a strong base such as sodium hydroxide, the dehydrohalogenation will occur, producing an alkene, where an elimination reaction will occur. Right, so below is structure of halogen of bromide react with the potassium hydroxide in ethanol, so it will release the cyclohexanone and the potassium bromide and water. Right, so you can see that this bromocyclohexane and reaction with the potassium hydroxide to produce cyclohexane is 80% yield, right? So now we can see there is two possibility. Substitution and elimination reaction is actually in competition. So we should now consider the determining factors after studying the mechanism of elimination. So first we need to look on the E2 reaction mechanism. All right, so this is the hydroxyl that will attack, right, the alpha carbon, right? And it will cause the releasing of hydrogen in beta carbon to produce the alkene, right? So the elimination of the E1 and E2, basically the reaction rate is the same for SN2 in E2, where we should consider that the rate is concentration of the alkyl halide and the nucleophile in E2 reactions. Okay, for the E2 reaction will occur when the secondary and the tertiary alkyl halide is treated with a strong base. So all strong bases like hydroxyl are good nucleophiles in secondary and tertiary alkyl halides. So the alpha carbon in the alkyl halide is hindered. So we know that in the SN2, right? So in such cases, a strong base will abstract or remove a hydrogen ion from a beta carbon. So before it hits the alpha carbon. So thus strong bases cause elimination E2 in secondary and tertiary alkyl halides and cause substitution SN2 in unhindered methyl and primary alkyl halides. So now we can see the differences. So in order how we can predict based on the tertiary or primary, based on the what we call this, the nucleophile, right? Right, for the elimination reactions, so in this case, the 1-bromo 1,1-dimethyl-ethane, right, react with hydroxyl group will produce 2-methyl-propene to release water and bromide. So the rate law is for E2 reaction is similar to SN2 reaction, where the rate is equal to the K constant times the 1-bromo 1,1-dimethyl-ethane times the concentration of the nucleophile or the hydroxyl. So in this reaction is an example of E2 reaction, where E is stand for elimination and 2 is stand for biomolecular. Thus, the E2 reaction For example, in this example of a structure of alkyl halide, so a proton is removed and at the same time the bromide is eliminated. So basically the mechanism of E2 reaction is a one-step reaction. Right, so from this one structure of alkyl halide, it will produce the products where the elimination of the bromide and water. So in the E2 reactions, so the nucleophile that will react with the hydrogen of the sigma bond formation, the carbon and the hydrogen the bond will be break, and the carbon of the pi bond formation and the carbon and the bromide or the bromine what we call this sigma bond will be break, all occurs simultaneously, and you can see there is no carbon cation intermediates are formed to produce the alkene, and the bromine and hydrogen is the nucleophile react bind with the hydrogen and release the halides. So the reaction in which these several steps occur simultaneously are called concerted reaction. So we will consider the Z-Ceph rule in E2 reaction. So we have to recall that in the elimination of alkyl halide from alkenes, the more highly substituted will be more stable alkene products predominates. So for example, this bromobutane we get with the ethanol and the sodium, right, ion. So it will produce two different butane structure, 2 butene and 1 butene, and we will consider the 2 butene as the major product. And based on the Z-Ceph rules, the alkene form in greatest amount is the one that corresponds to removal of the hydrogen from the beta carbon having the fewest hydrogen substituents. So we call back on the alpha carbon is the carbon that attached to the leaving group or the halide. And the beta carbon is the carbon that adjacent to the carbon attached to the leaving group. So in this case, the blue beta carbon has the fewest hydrogens, and therefore the alkene formed from this alkyl halide is in an elimination reaction would be this structure. So you can see that example of this structure of bromine or the alkyl halide containing in the form of 6 carbon ring. So we know that this is the alpha carbon and the adjacent is beta and beta carbon. So we know that alpha carbon is attached with another carbon, CH3, with beta carbon containing 3 hydrogens. And this beta carbon that adjacent to the alpha carbon has only one, right? Only one hydrogen. And this beta carbon has two hydrocarbons, right? So in the form of, in the presence of base or the nucleophile, so the product will base this structure. So the elimination will be occur at this beta carbon. So basically, the Z-Ceph rule, it is the elimination will occur such that a hydrogen is removed from beta carbon with the fewest hydrogen. All right, the E2 reactions are actually anti-periplanar. So we have seen the example below. So the E2 reactions basically do not always follow the Z-Ceph rule. So the E2 elimination will occur with anti-periplanar geometry, meaning the periplanar that all four reacting atoms, the hydrogen, the carbon, you see, and the halide are all lie at the same plane. So anti means that the hydrogen, see the hydrogen here, and the halide X, the eliminated atoms are on the opposite sides, right? So look at the mechanism again and note that the opposite side and same plane orientation of the mechanism. So we can see on the alpha carbon and the beta carbon are in the same plane, and the hydrogen that release and react with the base or nucleophile is on another carbon, and the halide is on the alpha carbon is on the other side, which release the to form the what we call this nucleophile and bind with the hydrogen and release the halide to form alkene. Right, sorry. Back to this anti-periplanar of iteration in cyclic alkyl halides. So this is the example of cyclic alkyl halide that we react with sodium hydroxide at E2 reactions. So basically, when E2 reaction occur in open chain alkyl halides, the ZSAF product usually cannot occur because of the single bond. It can be occurred because the single bond can rotate. However, in the cyclic structure, the single bond cannot rotate. So we need to mind full of the stereochemistry of the cyclic alkyl halide, which undergo the E2 reaction. Right, so below of the structure, this is the trans structure of 1-chloro-2-methyl cyclopentane, which undergo the E2 reaction with the sodium hydroxide. So basically, the hydroxyl group will attack at this hydrogen of the beta carbon, and it will attack towards this carbon of alpha carbon, right, to release the halide, which is the chloride, to form the non-ZSAF product, which is the major product, and release sodium chloride and water. So basically, the structure name is 3-methylcyclopentene. And there is also little or no ZSAF structure will be produced, right? And this structure is called 1-methylcyclopentene. Now we move on to E1 reactions. So basically, you have seen these reactions that occur in the SN2, right? And in SN1 reaction. So where the carbon cation will be occurred, right? Where the dissociation of the halide will cause the rate limiting or slowing down the reactions. Once the carbon cation occurred, there will be rapid elimination or substitution will be occurred, right? So just as in SN2 reaction, analogs to E2 reaction, so SN1 reaction have an analog to E1 reaction. So E1 elimination is unimolecular, first order. So the rate is constant times the concentration of the substrate or alkyl halide. So based on the figure above, so E1 elimination like SN1 substitution begin with unimolecular dissociation, but the dissociation is followed by loss of proton, right, in this reaction from the beta carbon, right, and attached to the carbon cation rather than the substitution. So meaning that E1 and SN1 normally occur in competition whenever an alkyl halide is treated in protic solvent with non-basic and poor nucleophile. So note that the best E1 substrate are also the best SN1 substrate, and mixture of product are usually obtained. Right? So this is the E1 reactions. So the 1-bromo 1-methyl-dimethyl ethane that will react with water to produce 2-methyl propene. So if the 1-bromo 1,1-dimethyl ethane is doubled, so the concentration of 2-methyl propene will not double. So this is similar to the rate law of the SN1, where the rate is equal to constant of concentration of the 1-bromo 1,1-dimethyl ethane, where the reaction is example of E1, where E is stand for elimination and 1 is stand for unimolecular. So in the E1 reaction, so you can see that the alkyl halide is dissociate, forming a carbon cation, right? And the water or the base will be removed, a proton, and the carbon cation will be produced. So the mechanism shows here that there is a two-step reaction, right? And the E1 reaction that you can see here is the two products, SN1 and E1 product. So based on the reaction of tertiary alkyl halide with the presence of ethanol at 65 degrees, so SN1 product is the major. So as the E2 reactions, E1 reaction also produce the more highly substituted alkene, follow the Z-self rule. However, unlike the E2 reactions, where no the carbon cation is produced, so carbon cation rearrangement can occur in E1 reactions, right? So you can see that in the example of this T-butyl chloride react with water in ethanol at 65 degrees, T-butanol and 2-methylpropene are produced. So in most unimolecular reaction, SN1 is favored over the E1, especially at low temperature. So such reactions with mixed product are not often used in synthetic chemistry, right? So in the E1 product, if the E1 product is desired, so it is better to use strong base and force the E2 reaction. So note that the increasing the strength of the nucleophile will favors SN1 over the E1. Right, so let's see the explanation. Right. So in the prediction of the the E1 mechanism, so non-basic good nucleophiles like the bromide and iodide will cause substitution, not elimination. Right? So in the tertiary substrate, only SN1 is possible. And in methyl and primary substrate, SN2 is faster. For secondary substrate, the mechanism of substitution will depend on the solvent. So strong bases like the hydroxyl and OR group are also good nucleophiles. So substitution and elimination will compete. So in tertiary and secondary alkyl halide, so E2 is faster. In primary and methyl alkyl halide, SN2 will occur. So weakly basic, weak nucleophiles like water, ethanol, and acetic acid cannot react unless a carbon cation forms. This only occurs with secondary or tertiary substrates. So once the carbon cation forms, both SN1 and elimination or E1 occur in competition. So the substitution product is usually predominant. So high temperatures increase the yield of elimination product over a substitution product. So the free energy change is equal to change of enthalpy minus the temperature in Kelvin times the change of entropy, where the elimination produces more products than substitution. Hence, creates greater entropy or disorder. Right? Polar solvents, both protic and aprotic, like water and the metal cyanide respectively, favor unimolecular reaction SN1 and E1 by stabilizing the carbon cation ion intermediate. Polar aprotic solvent enhanced by molecular reaction SN2 and E2 by activating the nucleophile. Now we try to predict some reaction of the mechanism. So we have this table with alkyl halide from methyl, primary, secondary to tertiary. And then we have several substrate and nucleophile. So the first one is good nucleophile in non-basic, and the example is bromide. So what we should predict? So since we know that it is good neutrophile and it is non-basic and it is a bromide, so we should consider SN2, right? Because it's unhindered, okay? And followed by primary, secondary. However, tertiary is SN1 because the tertiary structure is hindered at the alpha carbon. How about the secondary? So it should be SN2, right? For this good nucleophile with non-basic. Right, for good neutrophile with strong base and ethoxide. So the same, the metal is SN2 and primary is SN2 reaction. However, the tertiary will be E2 reactions, right, because of in strong base. And of course, the secondary also will favor E2 reactions. So next, on good nucleophile with strong bulky base, example T-butoxide. So the strong bulky bases like T-butoxide are hindered. Okay, so they have difficulty hitting the alpha carbon in primary alkyl halide. So as a result, they favor E2 over SN2 products. Right, so we know that tertiary is E2 and the secondary is E2 and metal will be SN2 and the primary will be either E2 or SN2 reaction. Now we look on the last example of very poor nucleophile, non-basic, and in the example is acetic acid. Okay, so if it's poor nucleophile, it can be SN1 or E1, right? So there will be no reaction for methyl because we know that SN1 we favor tertiary structure, right? So of course, primary will have no reaction as well. And for secondary is SN1 and E1 will be a mixture of product. And as well as the tertiary will be SN1 and E1 reaction. Okay, we look on another predicting other reactions of mechanism. So the nucleophiles in the table are extreme. So some nucleophiles have basicity and nucleophility in between this extreme. So the reaction mechanism that they will predominate can be interpreted with good success. So predict the predominant reaction mechanism, the following table. So we look on this, another example of alkyl halide. We look on started from methyl to tertiary. We look on the first one with pKb 4.7. The base is moderate. Nucleophile is very good. So what do you think for methyl? Should be SN2, right? So the primary is SN2. The secondary is or the tertiary is E2, and the secondary is SN2. How about the next one? PKB is 6 or towards neutral. The nucleophile is, the base is moderate. Nucleophile is very good. So basically the methyl will be SN2. The same. Primary is SN2. The tertiary will undergo E2 because of the moderate base. And the secondary is also SN2. Move on to next is with PKB with 9. Right, it's a weak base. The profile is fair. So methyl will be SN2. The primary is also SN2. The tertiary is E2, right? Elimination reaction 2. And also the secondary because of the weak base and fair nucleophile. And that's why the secondary is changed to E2 reactions. Now we look on the last table, which is a ratio with the hydrogen chloride, hydrogen bromide, and hydrogen iodide, which we assume to be in aqueous solution, a protic solvent, right? So we know that this reaction can react either SN1 or SN2, right? So based on that we have studied previously in the early part of the lecture. So we know that basically methyl will be SN2, right? Primary will be SN2 because they are not slightly hindered. And secondary, there is hindered, right? The alpha carbon. So it will be, the tertiary will be completely hindered. So SN1. And the secondary, of course, SN1. Right? Okay, next we look on the alkylation of alkenides, 3 double bond. So recall the preparation of long alkynes. So a terminal alkynes have pKa equal to 25, is deprotonated with a very strong base. So for example, here the alkynes that react with the sodium amine, right, to produce the alkyne that substituted with the sodium and release the ammonia. So the alkynide and ion is a good neutrophile which can substitute, replace halogen atoms in methyl or primary alkyl halide, producing longer terminal alkynes. So this is the same structure as previous, but this is a long terminal alkyne. So the reaction is straightforward with methyl and primary alkyl halides and proceed with SN2 mechanism. Right, so alkynide and ion also strong base with pKb equal to -11, as well as good neutrophile. So E2 will compete with SN2 for secondary and tertiary alkyl halides. So basically, we will see that the product will be more towards the E2 reactions. Right, so basically, the reaction for alkynides or 3 double bond will be similar, right, with SN2 and E2 reactions. So let's see some preparation of alkyl halides from alcohol. So this is Lucas test, which is considered as SN1 because we understand that this is a tertiary structure which containing the hydroxyl group, which will be ionized with deprotonated, right? And the alpha carbon will be form carbon cation ion, right? And release the OH group so that it will substitute it with the chlorine, right? So this is SN1. So alkyl halide can be prepared from alcohol by reaction with the hydrogen halide. So example, the substitution of a halide on a protonated alcohol. So basically this tertiary structure is rapid. So because of the carbon cation is stabilized by protic solvent, which is the water. Right, for the hydroxyl is a poor leaving group, so it is not displaced directly by nucleophiles. So reaction in acid media with protonates the hydroxyl group producing a better leaving group, water. So we know that in secondary and tertiary alcohol we react through SN1, but in methyl and primary alcohol we react through SN2. So below is an interaction of the primary alcohol, right? So there we know deprotonation and carbon cation will be produced. However, this reaction is very slow because of the protic solvent will inhibits the nucleophile. And shall we see the example? So how is the reaction of isopropyl alcohol with the hydrogen bromide? And also what is the product if the concentrated of the isopropyl alcohol react with the sulfuric acid, concentrated sulfuric acid, replacing the hydrogen chloride, right? However, the answer for this question, the mechanism of the isopropyl alcohol with the hydrogen bromide and also the products of the concentrated sulfuric acid is not appear in these notes. So I will attach the supplementary or the answer in the petroblast. All right. So we move on to the next slide, which is on the preparation of alkyl halides from alcohol that is actually can also be produced through a reaction with the phosphorus tribromide, PBr3, right? Which it transformed the hydroxyl or hydroxide group into a better leaving group, allowing the substitution SN2 to occur without rearrangement, right? And then preparation of alkenes from alkyl halides. So we know that the secondary and tertiary alkyl halides can be dehydrogenated with a strong base with hydroxyl producing an alkene. So we know that this bromocyclohexane react with potassium hydroxide will produce major product, cyclohexene. And clearly this is an E2 reaction. And this question also will not appear in these notes, but I will share, as I said, supplementary on the answer of this question, right? But basically, we know that can you predict the mechanism that occurs with methyl and primary alkyl halide, right? And then predict the products and mechanism that occur with isopropyl chloride and sodium hydroxide. The blue question, I will prepare the supplementary answer in the petroblast, right? Okay, so summary of SN and elimination reaction. So alkyl halide substrate reactivity. So you can see that towards from primary to methyl halide. So because of unhindered substrate, so it favors more SN2. So they do not form a stable carbon ion and do not react by SN1 or E1. Then towards secondary to tertiary, so hindered substrate. So the SN2 increasingly unfavored. So it will favor E2 is okay, means it's favored more E2. and then increasingly stable cation. So it will be favors SN1 and E1. So E2 is also favored. So you can see that iteration possible with strong bases and iteration will possible with strong bulky bases such as T-butoside. Right, for the reactivity of nucleophile, so you can see that the good nucleophile which are weak bases will favor SN reactions, and good nucleophile which are also strong bases will favor the reaction of these E1 and S1, SN1, right? So note that poor nucleophiles that are also weak bases, right? For example, like water and so on, do not undergo any reaction unless the carbon cation is formed first. So if a carbon cation can form, so basically the secondary, tertiary, benzylic or allylic will prefer E1 and SN1, right? So I highlight again the leaving group. So iodide is the most good leaving group because of it has low or very weak base as compared to hydroxyl, right? And amine, which is poor leaving group because of because they both prefer substitution and elimination reaction, unfavored, right? And competition between the SN2 and E2 and SN1 and E1. So you can see that is SN1 rate is concentration, the rate is the constant times the alkyl halide. However, the SN2 is considering both the concentration of alkyl halide and nucleophile. E1 is only considering the concentration of alkyl halide, and E2 is similar to SN2, right? So SN2 and E2 are favored by high concentration of good nucleophile or strong base, and SN1 and E2 are favored by a poor nucleophile or weak base. So because of poor nucleophile or weak base, this favors SN2 and E2 reaction. So this is some example of competition between substitution and elimination. So again, I highlighted that SN2 reaction will be favored from primary to tertiary, and E2 is vice versa from tertiary to primary. So you can see the product between SN2 and E2. So based on these reactions, so we can see that the SN2 is more favored than the elimination. The second reactions, we can see that the E2 is more favored, and the last reaction, E2 reaction is more favored than the SN2. So competition between substitution SN1 and E1. So basically all alkyl halides that react under SN1 and E1, both by substitution and elimination product are basically 50-50. So overall summary, the alkyl halide will undergo two kinds of nucleophilic substitution, SN1 and SN2, and two kinds of elimination, E1 and E2. So SN2 and E2 are bimolecular one-step reactions. SN1 and E1 are unimolecular with two-step reactions. SN1 will lead to mixture of stereoisomers. SN2 will invert the configuration of an asymmetric carbon. So the major product of an elimination is the most stable alkene. SN2 or E2 are favored by strong nucleophile or strong base. SN2 reaction are favored by primary alkyl halides. And lastly, E2 reaction are favored by tertiary alkyl halides. So I think that's all from me for this topic. So I wish you good luck for your exam. Okay guys, see you.